and also thank you very much for inviting me to provide you this series of talks this week. Well, it's needless to say that I was really looking forward to go there in person to the beautiful south coast of Spain. I just got to know that it's pretty hot there today. I mean, if I compare it to where I'm sitting right now, I mean, it actually started raining again and it's pretty cold. So thank you very much. Well, before I start this lecture, let me first give you a couple of warnings, let's say. Is that first of all, I mean, especially the lecture of today, and in part also the lecture on Wednesday, is mainly concerned with, let's say, my thoughts about the complicated issue of understanding electrical power. And I want to say beforehand that I don't want to make any claim whatsoever that my power theory, between quotes, is better than any other existing theory, or that it's more useful or even complete. And especially the last part will become clear during the presentation, I hope. Also, other people have said very important words, which I like to bring forward to you. I recommend that you keep this in mind during the presentation and mainly in your whole academic career. And that is this quote from Einstein, what he said like 100 years ago. And that is, as far as the laws of mathematics refer to reality, they are not certain. And as far as they are certain, they do not refer to reality. Well, that's a pretty heavy statement, but think about it. There is this other guy who is a specialist in measurement theory and applications. And of course, I mean, measurement is, especially in electrical power, is perhaps the main reason why many people have in their career, or at least devoting a lot of time in looking at these power resolutions and trying to understand them. And well, you can read it for yourself, of course, but what you see is, in the first sentence here, physical reality is disaster. And this also applies when we are dealing with electrical power, and especially when we want to understand it. And here is part of the quote which I put in red, and that is a bit in like, let's say, a funny way, in the sense that I will especially focus today on imaginary numbers and imaginary functions, or complex functions in general. And well, take this into account when you hear everything what I'm about to say. Okay, so as said, I mean, this workshop for this week consists of 3 days. Today I will talk about Hilbert transform and power resolutions. The second lecture on Wednesday is completely devoted to the concept of reactive power. And in the third lecture on Friday, I'd like to talk about a couple of things, and I will start with this the use and also well, let's say the abuse of this lossless LC filters you see often appearing in papers on improving power factor. And I will also introduce some things that my colleagues and myself are dealing with at my university. But let's see how this week will turn out in the end. Let's start with this Hilbert transform and power resolutions. So, to give you an overview of the motivation of this work, it's like that in the classical electrical engineering community. I mean, this resolution, what I've put in my title, what it's referring to is actually this decomposition of, actually, this was just decomposed the active power and the reactive power. And in the old days, I mean, this was working reasonably well for many occasions at least. And also mathematically, I mean, this is like totally undisputed, we could say. I mean, this is what you learn as an electrical engineer in undergraduate studies. You learn about these three objects, and also the ratio between P and S as the power factor. You can find it in almost any standard textbook on electrical engineering or power engineering. But the problem starts when we have let's say, distorted currents and voltages, non-sinusoidal conditions. And that's what we face in like the last couple of decades in an increasing manner with all the power electronics which is entering our homes and entering the industry. And then what you see in the literature is that people who are trying to deal with these issues of this power trinity not being complete enough, let's say, that they all dance around decomposition of the apparent power mainly in this way. So we more or less all agree that active power is something that we can even like practically verify and confirm. But then, I mean, usually like a discussion already starts around the definition of reactive power when you have distorted currents and voltages. And then you see that with these three components, we're not finished. I mean, we need to introduce extra term, which I denote here as rest 1 and rest 2. And to give you one of the earliest ones is from Constantin Buriano, who needed to introduce like a distortion power in order to complete his right angle triangle. He made it like multi-dimensional. And moreover, and that's by Leszek Czarnecki, who developed this current physical components power resolution. He needs 5 components in order to make like a right angle triangle. And well, if you look at the current IEEE standard, which was introduced in 2010, I mean, it's up to 11 components even, and this includes also 3-phase systems, like over here. So there is one problem already here, and that is that this kind of power resolutions, they are based on frequency domain techniques mainly, so on Fourier analysis. And if you think about this, I mean, of course, this is a beautiful mathematical theory, but suppose I say just hello to you, and you record that signal. That if you do like if you have a spectrum analyzer and you analyze that word hello, then you get a certain spectrum. But I can think of many other sounds that have absolutely the same spectrum. So the spectrum is, in that sense, it's not unique, and also the different sounds with the same spectrum will reach my ear in a different way. So my ear and my brains, they interpret that in another way, right? So in that sense, Fourier analysis is like, there is some ambiguity, let's say. It's not a unique way of looking at things. So, and that's like that's one of the motivations. And another one is that, well, you see already in this in these examples of currently existing power resolutions, and that they are mutually inconsistent. These rest terms, people are fighting over them, what it should be, and already the reactive power. There are many definitions. I mean, there was a report from the NIST in 2011, where they had 11 definitions of reactive power already. I mean, that raises a lot of questions, right? And in my opinion, many of these problems are due to the fact that these resolutions are based on like an averaging procedure. So the physics, if anything at all present, is usually averaged out. So what happens within a cycle of an energy transfer is usually just averaged out, and then you try to do some orthogonal decomposition. And once you define the power, then it seems that we understand it. But that's of course not really the case. So the contribution and also the scope for all my lectures actually are restricted to single phase systems, because it's just for brevity. I mean, many of the things I will introduce will carry over also to three phase systems, of course, but I will restrict to single phase ones. And what I try to contribute with this is that that we have a deeper mathematical insight into the concept of a phasor. That should be known to any electrical engineer. But I'd like to introduce really the mathematical underlying framework where this comes from. And I will also introduce a power resolution that can be directly obtained from the energy flow, so from the instantaneous power profile. And eventually this will lead to, again, a power trinity, but then a power trinity which is varying in time. And what this enables us is to have a local physical picture and also a local time scale on how we can look into the energy transfer of one cycle, or more cycles if you want, but we can look, we don't discard anything. Okay? So, and especially the time scale, we will see that is a very important thing anyway when you analyze things like energy transfer. Well, in the end, I hope that it sheds some, it gives some insights, and it sheds some new light on like load characterization and quality. That in the literature you usually see this denoted as power quality. But power quality is a bit of a strange buzzword, in the sense that, I mean, can we really define quality of power? I mean, do we not rather talk about like the quality of a load or the quality of a supply? But okay, I'll leave for another time. Okay, let's look at the physical picture of the situation. So what we have like here we have like an energy supplier, so you can consider this like a generator, and then you have the transmission lines, and the energy which is converted here from I don't know, some kind of fuel that is transported to consumers, or like a whole bunch of consumers. And what we are interested in is that if we put measurement equipment at the point of common coupling, the PCC, where we measure current and voltage, and that we can say something about the efficiency of this energy transfer. So from a physical perspective, if I can measure the current and the voltage over here, then the energy is given by this equation, where this T0 is the moment that you start measuring. This equation is essentially just built into the utility meter at your home. It's an equation like that, but then turned into some practical device who records it. And so we have some start at the energy, which at the point that we start the measurement, and then the rest evolves over time. We call that the little w of t. Okay, if you look at the rate of change of energy, that gives you power, right? And that is actually the dynamics of the whole thing. I mean, power, if you translate it back from Latin, that means dynamics, essentially. And that's what's reflected over here. And what is very important to note here is that these two definitions of energy and of instantaneous power, they are valid for any waveform or load. It doesn't matter if it's linear, time varying, or non-linear, or whatever. I mean, you just measure the current and the voltage, and you can just define what is the energy transfer at that point in time. But what we usually do is, and especially when the voltage and the current waveforms are periodic, with some common period time, which I denote by a capital T, and we can call that one cycle of the energy transfer, and we can define something what is called active power, and that is just the average of the instantaneous power, the rate of change of the energy. And here, I mean, again, T naught, that is the instant when the measurement starts, and then this constant, this integer, positive integer k, and that just represents the number of cycles. We have some standards for that, some norms, how long these measurements are usually to be taken. I come back to that later. So, okay, I just explained that is valid under any condition, essentially. And active power, I mean, that is most easily you can when the waveforms are periodic, and if they are not periodic, then at least mathematically you could take the limit of the cycle to infinity. But it's not very practical, of course. But mathematically we can get an answer. But classically, how people have been looking at the problem is as follows. Suppose that at the point of common coupling, so over here, that we have a perfect sinusoidal voltage with a root mean square, an RMS value, or an effective value, denoted by capital U, and I take the initial phase to be 0, and the omega naught, that is the fundamental frequency. So in Europe, that is like 2 times pi times 50 from 50 hertz, or in the US, they work with 60 hertz, for example. So I call with omega naught, I denote just the fundamental frequency, the most significant energy carrying frequency. And then suppose that the current here is of this form, so with an RMS value of capital I, and then same frequency, and then there is some phase shift possibly. Now, using some trigonometric identities, you can decompose the product between the voltage and the current in this form, and this is what you often see in the standard textbooks. And what you see is that this instantaneous power is then fluctuating at 2 times the fundamental frequency. So in Europe, that will be 100 hertz, right? And you have these two guys over here again, the active power, and this one is what we usually designate as being the reactive power. The definitions are given over here. I did this dot, this way of writing. That means like def. But sometimes I like to also use it like this, and so then you see this gives a direction of what is defining what. Okay, just a mathematical little thingy. So active power and reactive power. Now from this we can also define the apparent power, and the apparent power is given over here. Is essentially just a Pythagorean relationship. And you see that the cosine squared plus the sine squared, that equals 1. And so you just end up with the product between the RMS values of the voltage and the RMS values of the current. And from here you can also define what is known as the power factor. It's the ratio of the active power with respect to the apparent power, which in this case, in the purely sinusoidal case, that coincides with the good old cosine of phi. And phi is then the phase shift between the voltage and the current. Well, these two definitions, they also extend to non-sinusoidal waveforms. I mean, you can even buy meters in the shop who measure what is sometimes referred to as true RMS. That's a bit of a strange way of saying it, because in my opinion, RMS is RMS, and in the purely sinusoidal case, I mean, you can pretty easily obtain it by measuring the maximum value of the sinusoid and divide it by the square root out of 2. But in general, I mean, it's just you take the square of the signal, and then you take the average of the cycle, and then you take the square of it. That's the way it's defined. Okay, so this is the classical setting, but already a very long time ago, and actually it was 1890. Then Steinmetz, you probably know from the Steinmetz equivalent circuit of an electrical machine, and he also did a lot of research in hysteresis and lightning, and a lot of people also think that he introduced the concept of a phasor. Well, that is only partly true. I don't want to go into details, but I mean, that came from others before, and he has been adopting it, but he also has been against it for a while, at least to my knowledge. If you want, there is a paper by Harold Kirkham dealing with the historical issues surrounding phasors. But the same guy, Charles Proteus Steinmetz, he also noticed that there was you had this arc bulbs that were old let's say just lamps, where if they were measuring the voltage and current, what they saw is something similar as what I show here. This is a simplified version of it, but you just have a steady voltage, and I just normalized it here. But you have a steady, purely sinusoidal voltage, and then this arc bulb, this arc light. What it was showing was like a current, which appeared to be in phase with the voltage, but the amplitudes were changing. So this is like a time varying conductance, you could say. Yeah, so it is something like something like this. So this is the current, the voltage, and then I have a time varying conductance, right? So there's this situation. Well, if you apply what I previously defined as being the apparent power and the active power, this is periodic waveform, so we can define the RMS values and we can define the active power. Then you will find that the power factor for this situation is less than 1. And this has been very disturbing for a lot of electrical engineers, because if you think in linear terms, I mean, this is a linear relationship, right? The only thing is that we are dealing with a time varying device, but the relationship is linear. So what happens is that apparently, like a resistor, a pure resistor, even though it's time varying, will give you a power factor that is less than 1. Okay? And this was already puzzling Steinmetz, because they had this situation of this was known, S squared is P squared plus Q squared. That was known at that time, and that was figured out also mathematically and more or less well understood. But the problem is, I mean, there is no phase shift over here. So that means that it is 0, right? So that leaves something undefined in order to make like this equation work, right? So what Steinmetz have been introducing is what they call a Butler component, which is given by this. It's just the residual between P and S. And the whole thing is centered around the Cauchy-Schwarz inequality anyway. And he was denoting this as an effective reactance. Well, in the meanwhile, a lot of people have been looking at this situation and came up with all kinds of stuff. But what you see in the majority of publications and also like the current IEEE standard is that this effect of the power factor being less than unity, that will be attributed to a distortion power. So some kind of power which is due to the distortion in the current or in the voltage or whatever. And also in this framework of the current physical components by Czarnecki, this non-active power component is also contributed to some kind of distortion power, but he calls it a load-generated harmonic power. Okay? Well, here a first problem pops up, and you can already find out. Well, he wrote everything in French, so made some translation, or actually I borrowed these two slides from Harold Kirkham, which is the chairman of the current of the working group for the revision of the current standard. And if you read this very carefully, what you will observe is that Buriano is talking about distortion power and also reactive power, and he say it's an imaginary power. That's one thing. So that's already a bit from a mathematical perspective. You can think of like, okay, like in a complex number, like imaginary part of a power resolution or whatever. But then he's saying something peculiar, is that he attributes the reactive power to the energy between the circuit and the external environment formed by the electrostatic and the electromagnetic fields. And that is also, according to him, the reason that this energy has a non-zero finite average value. So that will be then the reactive power. But here now, carefully read this and think a bit about it, then the distortion power has nothing to do with the electromagnetic fields anymore. So this is, of course, a major. We all know from let's say basic courses on electromagnetic field theory, where we have the Poynting vector, that without a field to carry it, there cannot exist a current, right? So the postulated current associated to the distortion power, because essentially these power resolutions, they are rather like a current resolution than a power resolution, because you just if you do the deposition in an orthogonal way, then you just have that you can sum the squares and you multiply it by the RMS value of the voltage, and then you get your power balance, your power resolution, right? So essentially, all this stuff is a current resolution. But I mean, if there is no field, such a current can simply not exist. Well, if you want to know more about this, Harold Kirkham, he published a very nice paper, also explaining all the historical, a lot of historical facts surrounding this distortion and also the reactive power. Then you can find more information on this. So this distortion power is simply something that doesn't make any sense in physical reality, and for that reason, I can already tell you that in the coming revision of the IEEE standard, this will just be taken out. Another example is this one, and this was what I was referring to when I was defining the active power, that you have standards which tell you for how long you should do the measurement. Well, usually if you do this, the active power or the RMS voltage or RMS currents, you take like 10 cycles for 50 hertz signals and 12 for 60 hertz. So then you have like a measurement cycle of 200 milliseconds. Now, suppose you have a situation that you have a linear load, and that you measure at like you do this measurement like 4 times, but this load is maybe varying in time, so linear time varying. So this is suppose that this is what you measure over here. So you see that things are changing per measurement. Yeah. So according then to the IEEE standard, I mean the apparent power, you can compute like this. You just take the root of the sum of the squares. That's what you can. That's just allowed to do, also mathematically. So this is what you get. With the total active power, you can just take the average of all the things. You sum those 4 measurements and you divide them by 4. And with the reactive power, since it's all positive, you can also come up with like a total reactive power of this, taking over the net reactive power taken over those or derived from those 4 measurements. Well, if you square this quantity and you compare it with the sum of the squares of these 2 quantities, you will notice that there is no equality, and that's really strange, right? Especially when I think about a linear circuit with sinusoidal voltage and sinusoidal currents. Well, this was the reason for the previous chair of the IEEE working group for the 2010 standard, that was Alexander Emanuel, to introduce this thing called randomness power. That's like the residual that fills the gap to make this equality work. But this is again like some kind of, I don't know what kind of power, like a distortion type of power, which based on physical grounds cannot exist. Well, the whole thing, especially of interest to energy suppliers, right, is that if you consider like this first example I gave, where you have this current which is fluctuating in amplitude, of course it draws a certain amount of active power. Okay, well, this power is like withdrawn in a fluctuating manner. Well, from like the point of view of the losses over here, it would be much more preferable to withdraw the same amount of active power in a way such that the current waveform is exactly in phase. In mathematics, you call it collinear. So it's just in parallel, let's say, with the supplied voltage. So then you get like this definition, which was one of the first one, I think, was like Friese, who introduced this in like the early 1930s. So this is just actually the first step in this in the standard Gram-Schmidt orthogonalization procedure. This is just a projection of the current you withdraw projected on the voltage, and of course, I mean that once you only withdraw like the current in parallel to the voltage, I mean that will minimizes the R. I suppose that that you have resistive losses that will just reduce the Ri squared thing, like reduced power losses, if you fulfill this. Of course, when you then what is classically done, you place like a compensation capacitor here. But if you take these losses into account, you have to be careful that the voltage doesn't go up too much. So this, from an optimization point of view, when you consider these losses, then this is not the most optimal thing you can do. I mean, there are some recent results by Alexander Stankovic, for example, about this. Anyway, so I propose now to really take off. And let us start from scratch to build up the framework I want to share with you. And now I go I read up a little bit, because a lot of things here, I mean, should, if you're an electrical engineer, should already known to you. But just to set the stage. So I would like to concentrate on phasors, which are like a particular complex number, essentially, and you can extend them by making it a rotating vector. That's actually what I would like to call a phasor. Well, there are a couple of advantages, and that is that we know that in steady state, that we if we use this phasor notation or complex, we can just drop the differential equations, and we can just use just linear algebra to solve our problems. Well, this is true in most of the cases, and on Friday I will come back to this, especially when we networks, and this will introduce a couple of things that you cannot find in text, circumvented somehow. But this phasor concept that has led to this important concepts of impedance and admittance, and also to the notion of complex power, and that will be the main topic of the remaining part of this presentation. So okay, so roughly speaking, I mean, a phasor is very often derived by starting from one of the many equations Leonhard Euler introduced to us, and this is one of them. This is perhaps his most famous one. And that you have this complex, or in this case, this imaginary and decomposed in a real part and in an imaginary part, which just reflects the cosine function and the sine function. And this J here, that is just the imaginary unit. So this equation, you can play with it, and that indicates that, for example, a cosine function. So let's take like this one with a certain amplitude that we can represent it mathematically as the sum of two complex valued functions, these two things. With the sinusoid, you can do the same, but then this will be a minus, and then you have 2 times j. Yeah. So I can also then take the real part of one of these and say, okay, well, if I take the real part of this one, for example, then I can write it as the real part of the product of this part and a function of t, right? Well, the last part is this exponential of the where t is included. I mean, that is what I call a rotating unit phasor. And if you multiply that by a constant, say the amplitude or something, then you can just stretch it. But essentially, this unit phasor, it rotates in the complex plane with frequency omega. Yeah, and the theta here I took theta as 0, but theta is just the 0. Then the projection from the real from the real axis into the time axis, you get the cosine, and the projection from the imaginary axis onto the time axis, you get the sine. That is the same as what you saw here, but now for a more general argument of the exponential here. Okay. So, well, mathematicians, they denote this term as the analytic representation of this real signal over here. This is a complex signal, and this is a real signal. And engineers, they often denote it as a rotating phasor. Well, I use both, and we'll just end up with something what is called a time varying phasor, a generalization of this whole thing. Yeah. Well, as said, the use of phasors brings a significant mathematical simplification, and especially when you consider differentiation and integration, and that's also how you obtain like impedance and admittance of network components. So here it's briefly given that suppose I have this phasor over here, this rotating phasor, with the steady phasor over here. And then you can take the time derivative, and that's simply given over here. And if I take the time integral of this thing, then I get this result. And what we observe from this is that the derivative of a phasor that is just is multiplying the original phasor by the frequency, by omega, and it makes the resulting phasor leading the original one by 90 degrees, or pi over 2. And integration that does the dual thing, that is scaling with respect to the frequency, and you just add a 90 degrees lag. Yeah, so minus pi over 2, let's say. And from this, you can define the impedance, and it goes pretty straightforward. Here you have the two rotating phasors. And then impedance is just defined as the ratio between those phases. And then you see that indeed the time dependence for sinusoidal signals is dropping out. And then you just obtain this complex representation. The impedance is essentially just a complex number depending on the frequency. But time is taken out because, I mean, for sinusoidal signals, I mean, time is not important anymore in that sense. It always repeats itself in the same way, according to purely sinusoidal movements. Now, the admittance is just the reciprocal of the impedance, 1 over z in this case. Now, here I put it in a table, and this should all be well known to you. But it's based on this. You have to start from the rotating ones in order to get the frequency dependence in your impedance definitions for resistors, inductors, and capacitors. Okay, I will come back to this in more detail in the third part. So how do we derive something what is called complex power? Well, let's consider again some one-port load where we have different phasors given over here. And so now I give the voltage also some initial angle, some starting angle, and likewise for the current with alpha and beta here representing that. And U, capital U, capital I, and the RMS values. So let's define the phase difference to be phi, just the difference between those two angles. And then we can introduce this, well, weighted complex inner product. And that's given over here. So if you work that out, you fill just in all these things over here, and you write it all out, you end up with something like this, where the active power appears as a real part, and the reactive power appears as an imaginary part. And this is what is called the complex power, here denoted by a bold-faced capital S. Here, you can actually construct a power triangle. And this is, in my opinion, the only correct way. You sometimes see just like triangles without mentioning that we are talking about imaginary and real parts. But then if you think about these, the fact that P is like also an inner product and things like that, and that doesn't make any sense. It only makes sense when you define this in the complex plane. And then you see here the imaginary part reflected by the reactive power and the real part by the active power. And the length, this is actually a complex number, and the length of that is the apparent power. And the complex power is the whole thing together with the magnitude, the length, and also the angle. Yeah, and from here we obviously can get again the classical Pythagorean equality given over here. All right. Well, if you look at this example, where I have some generator who provides, without any losses in this case, provides energy to let's say an RL load, which we can compensate by some power factor correction capacitor. That's why I put it in red here. If you work this out in terms of these phasors and in terms of these complex powers, then what you will find is that this is the active power. That's just the energy converted, or the power converted by this resistor into heat or into work. And then the imaginary part looks like this. And this, in my opinion, is maybe the best we can do for an interpretation of reactive power. And in some classical books you find it. And that reactive power is due to the fact that there is an imbalance between magnetic and electric energy. So an imbalance between energy stored in inductors and energy stored in capacitors. And this is exactly why this power factor correction in the sinusoidal case works so perfectly. Because what we do is that if there is no capacitor here, so we just have a resistive inductive load, then we have just an excess of magnetic energy. Or actually, this is like a mean value of like from an average perspective, we have an excess of magnetic energy, right? And then we can compensate that excess of magnetic energy. We can compensate that by just adding electric energy. So that this difference, if this goes to zero, that means that the reactive power will be zero, and there is no phase shift. Yeah, so classical power factor correction using capacitor banks, that is actually just an energy egalization process, essentially. One question that you don't see to be answered in the literature is why did we not simply take the product, the direct product between two phasors? You have to take this weighted complex product like this, right? Taking the complex conjugate of the current, and we had to fix this by a half here. Well, just do the math. If you just do the direct computations, you get something like this, and then you see two time-varying terms which average out to zero. Both average out to zero, of course. So that doesn't work, right? So then if we just start from the time domain and we do the whole calculations again, so we can use the trigonometric identities like this. and then we can write it in that way, or we can also write it in this way. And then you see here is a part which is always larger or equal to 0, and this is then the fluctuating part where this reactive power is appearing again. And then if you take the average over one cycle, and then you get the active power, which is then non-zero. So somehow this half times this weighted complex in the product is like constructed based on stuff we like to. There is a much more deeper meaning, but I come back to that later on. Okay, so what you observe from here is that this capital P, the active power, is really an average, a mean quantity of is also fluctuating over time. This part has a zero mean, but you add a 1 here, so then the average here is 1, and you multiply it by P, so that indeed gives you this if you evaluate this integral. And here you have also this time varying quantity, but then here you see Q as being the maximum value. So that suggests that this reactive power is not a mean quantity. But that's of course very strange, right? Because we had S squared is P squared, for the purely sinusoidal case, plus Q squared. So then I am just comparing apples with oranges, right? Because if this is an average value and this is now all of a sudden like a maximum value, I mean, this is really strange, right? Maybe I can do it in this complex fashion. Then I had the complex S is P plus JQ. Here you do already an orthogonalization, so yeah, then it's not so strange if here I have apples and there I have oranges. That's allowed somehow. I mean, mathematically speaking, there is not much this. And to already make a little introduction to the lecture on Wednesday, I mean, this is also strange. We measure S in volt amperes, and that's apparently equal to another unit, which is called just the watt. Yeah, and that is summed with what we call the volt ampere reactive squared. So this is really you have apples, oranges, and pears or something. Yeah. I will actually show on Wednesday that this is pretty fine, but you need something very special to do this formally, at least. I come back to that later on. So if I just now assume that if this is a mean, then these two things must be mean quantities as well. Like otherwise, this equation doesn't make any sense. So then the question is, what kind of mean values are we talking about? Well, let us return to this way of decomposing the. There's this. Here we have like a generally a non-zero part, and here we have a fluctuating part. So this first term I recognize as the active power, and this thing, of course, is equal to the apparent power. So I can write it like this. And then if you compare this to your instantaneous power profile, then what you observe is that the green line here, the blue line is just the product of voltage with current. Then the green line is just the mean of this fluctuating signal, and then from the mean value to the maximum value, that's your apparent power. So what I can now introduce is what I call P plus and P minus. So this is just the measuring the distance from the origin to the maximum value of your instantaneous power, and this one is just measuring the distance from 0 to here, and I just take them both positive. That's why I put 2 arrows here. Let's say the length. Well, what we can do then is we can play a little bit with it, and then we see that, well, P plus is just the active power plus the apparent power, and we want to put just the absolute brackets around it, and P minus is P minus S, active minus apparent power. And you can rewrite this and solve these two equations. I have just two equations with two unknowns. I can solve for S, and that appears to be like this. And I can solve for the active power, that appears to be like this. Well, it's well known from mathematics that a quantity like this is what is known as an arithmetic mean quantity. So this shows that S is indeed a mean quantity. We already, of course, know it by the fact that it's that apparent power is the product between the RMS value of the voltage and the RMS value of the current. But there you have like two mean quantities which you multiply with each other. So then the question is, is the product of two mean quantities, is that again a mean quantity? Well, indeed it is, but it's an arithmetic. Yeah? And this, the active power in terms of these maximum and minimum values, is what we call a median. Yeah. This quadratic between active power, and if you do that and you work it out, what you get is that it's simply the product between, well, if I want to know Q, then I can take the root of it, but then I have to show that it's non-negative, right? So that's why I put this absolute brackets around this. But what you see here is that reactive power is the geometric mean. The geometric mean of the maximum and the minimum values. And you can easily show that by applying the chord theorem. It's actually this whole power trinity, the way we defined it, is just centered around the chord theorem in that sense. And so this picture you can see as if you look from the side into this instantaneous power profile. And then you define your Q. And depending on the ratio of the current and the voltage, that defines the direction in which you can define your reactive power. Like usually, you see here that if this is the classical definition, and if you see that if phi is positive, then the current lags the voltage. That's in case of an inductor. And when the phi is negative, then it leads the voltage, which is the case of a capacitor. Yeah. So if you put it in a Lisa-Joule plot, you just put current against voltage, and then you can just see that if it goes this way, then it's positive, and if it goes that way, and based on the rate of change of this angle, the sign of this, the rate of change of the angle, we can also put a sign to this Q. So that just a little factor, or let's say a qualifier in front of this geometric mean quantity. Okay. Well, we can go a little further, and it's also known in this mean theory that the arithmetic mean and the geometric mean they always satisfy this inequality. So that means essentially that S is larger than Q. That also holds in our case, and then you can see that it holds with equality if the minimum values, and that implies, of course, that the apparent power is equal to the reactive power, and that there is no, and that's in the lossless case for an inductor, a pure inductor or a pure capacitor as a load, and that there is no active power dissipation. And from the same perspective, we can also define the power factor, of course, which is the ratio of active power over apparent power, and that's then given over this, from which we see that it's 1 if there is no negative, if the instantaneous power profile doesn't go below the 0 line, and if it's 0, is that the instantaneous power is purely balanced about the origin, about the 0 line.